A fragile plant dye made it through centuries of rain, heat, microbes, and neglect, and that alone should not have been possible. Indigo fades easily, especially on exposed walls, yet Maya artists transformed it into a turquoise pigment with extraordinary staying power. Historic samples have resisted solvents, alkalis, and even aggressive acid tests. The color still glows across pottery, sculpture, codices, and ruined murals. Here's the answer in one sentence. Heat separated indigo into individual molecules and brought them into unusually close contact with microscopic channels inside a fibrous clay. And that partnership is what let Maya blue survive. The clay did not just carry the color, its structure changed what the color could survive. That answer sounds simple, but it took scientists nearly a century to work out, and 2 studies published in 2025 showed that the story is still changing. One tested temperatures from 100 to 500 degrees Celsius. Another traced the clay inside Maya blue across roughly 375 kilometers. Together, they showed that this pigment was engineered on 2 scales, inside a mineral and across a human network. Archaeologists first recognized the unusual pigment at Chichén Itzá in 1931. Its blue-green color remained visible on murals exposed to a punishing tropical climate even as other pigments weakened. Researchers exposed samples and reconstructions to acids, alkalis, and organic solvents, and Maya blue resisted many of those attacks. Calling it indestructible, though, is a nickname rather than a scientific fact. Intense acid treatment under reflux can damage both the pigment and the clay. That correction makes the achievement more impressive, not less. The Maya created this durability without modern polymers or sealed museum cases, using materials gathered from the living landscape. The pigment appears by roughly 50 BC and stayed in use through the colonial period, with related traditions surviving as late as the 19th century. Yet no ordinary mineral pigment behaved this way. Solving the mystery meant separating one color into 2 unlikely ingredients. The first was indigo, an organic colorant obtained in Mesoamerica from plants including the añil shrub, Indigofera sufferticosa. The leaves do not begin as bright blue pigment. Processing releases colorless precursors that later oxidize into indigo. But indigo alone could not explain Maya blue's resistance. The second ingredient was palygorskite, a pale fibrous clay containing narrow channels through its mineral structure. Those channels measure only about 3.7 by 6.4 angstroms. At that scale, molecular fit matters enormously. This produces a counterintuitive result. A related clay called sepiolite has wider channels and admits indigo more easily, yet the Maya blue-like pigment it produces generally shows weaker acid resistance. More room does not automatically mean better protection. The tighter fit can produce the stronger partnership. Laboratory work produced a similar pigment using palygorskite, very little indigo, and moderate heat. Some successful reconstructions need only 0.5 to 2% indigo. Knowing the ingredients, however, was like identifying flour and water after finding bread. The decisive question was, what heat made them do to each other? As palygorskite heats, it loses some water from its structure. Aggregated indigo separates into individual molecules that interact with channels, grooves, entrances, and surfaces in the clay. Many studies support at least some indigo moving deep into the nanoscale channels, where confinement, coordinated water, and several possible forms of bonding help stabilize it. Precision matters because scientists still debate exactly where the indigo sits and which mechanism dominates. Models place molecules inside channels, at their entrances, within grooves, or across several locations. Some researchers also propose that part of the indigo oxidizes into dihydroindigo, helping create greener shades. Other spectroscopic studies have not confirmed that compound, so the disagreement remains open. The newest temperature experiments sharpened the broader picture. In 2025, Wanjun Zhuang and his colleagues heated synthetic mixtures between 100 and 500 degrees Celsius for periods ranging from 1 hour to 3 days. They identified the strongest general window between 100 and 200 degrees, with heating times no longer than 8 hours. As the temperature approached 200 degrees, the pigment became greener and less blue. Above that point, color saturation fell sharply. Color therefore becomes evidence. A shade of Maya blue may preserve clues about the heat, duration, clay, and atmosphere used to make it. Despite the unsettled details, the broad mechanism remains secure. Organic dye and inorganic clay form a tightly interacting hybrid material. The clay protects the dye, and the dye supplies the color. Researchers call this a nanostructured material because its behavior depends on nanoscale architecture. Maya artisans lacked the language of nanoscience, but their practice controlled matter at that scale. A laboratory furnace can show what heat accomplishes. It cannot tell us how ancient people managed the process. For that, researchers examined a vessel pulled from Chichén Itzá's Sacred Cenote, a water-filled sinkhole that received ritual offerings and human sacrifices. Historical accounts describe some victims being painted blue, while archaeological evidence connects the pigment with offerings and sacred performance. Anthropologist Dean E. Arnold encountered a museum catalog label reading, "Blue on copal and bowl." It described a tripod bowl Edward Thompson dredged from the cenote in 1904. Roughly 20 centimeters across, it held hardened copal, an aromatic tree resin burned as incense. Beneath the copal were dispersed blue and white regions. Microscopy and chemical analysis found evidence consistent with indigo and palygorskite. Arnold and his colleagues concluded that the bowl may preserve an interrupted attempt to make Maya blue by heating its ingredients with burning copal. In that scenario, chemistry and ceremony were not separate. The ceremony created the material. Still, the evidence does not prove every batch used copal. It supports one method in one ritual setting, and researchers continue debating which methods serve different places and periods. The cenote held another clue, far larger than one bowl. Thompson recorded a blue silt layer roughly 4.5 to 5 meters thick beneath the mud. Maya blue does not adhere permanently to every surface, so pigment washed from objects, offerings, and people could accumulate in the water. The deposit records repetition. Generation after generation returned with objects, incense, and blue. Blue and green could evoke water, vegetation, jade, fertility, and renewal. Copal was sacred incense, while palygorskite had medicinal and ceramic uses. Earth, plant, water, smoke, and color entered one performance. Symbolism alone was not a technical manual. The Maya still needed the correct proportions, preparation, temperature, atmosphere, and time. Too little heat left the partnership weak. Too much degraded the color. The real lost technology was never merely a list of ingredients. It was practical judgment carried by people, places, and repeated acts. A second 2025 study revealed how far that judgment may have traveled. Dean Arnold and his colleagues analyzed 17 blue-painted pottery samples from Buena Vista del Cayo in Belize, dating between approximately AD 680 and 8680. 3 early samples contained unusually high calcium levels, possibly because the blue had been applied over thin plaster. The remaining 14 later samples matched palygorskite from Sakhalin in Yucatán, about 375 km away. That result changes the scale of the story. Maya blue was not always made from whatever clay happened to be nearby. A community could receive imported palygorskite, finished pigment, specialist knowledge, or some combination of the three. The researchers argue that these may have moved through restricted ceremonial or political exchanges rather than ordinary trade. The technology was material and social. Its strength depended on molecules fitting inside clay. Its survival depended on people maintaining routes, relationships, and memory. When those chains broke, the recipe survived only as residue. Losing the practice did not erase what the material could teach modern science. Maya blue became a blueprint for stronger colorants. Material scientists copied its guiding principle. A vulnerable molecule can gain new properties inside a protected mineral host. They have applied that strategy to other clays and porous materials. This approach is sometimes called archaeomimetic design. Instead of copying an ancient object's appearance, you copy its material strategy. Maya blue also warns against easy answers. Identifying indigo and palygorskite did not end the research. Experiments still test molecular placement, water loss, oxidation, bonding, temperature, and atmosphere. Color, acid resistance, and light stability can respond differently. No single factor controls every property. X-rays reveal mineral structure. Spectroscopy tracks molecular changes. Trace elements can reconstruct the movement of clay across hundreds of kilometers. Yet instruments recover mechanisms, not the entire human tradition. They cannot identify every craftsperson, gesture, prayer, or workshop variation. The color survived more completely than the knowledge system that produced it. That difference is what lost technology actually means. Maya blue was not magic, and it was not evidence of outside intervention. It was observation refined across generations. Maya makers learned that a plant dye, special clay, and heat could cooperate. They created durability by arranging ordinary materials into an extraordinary relationship. Modern chemistry named that relationship organic-inorganic hybridization. Modern instruments revealed its nanoscale structure, but those names arrived long after the achievement. The deepest lesson is not that ancient people possessed mysterious modern machines. It is that sophisticated technology can live inside craft, ritual, exchange, and practiced memory. When that memory breaks, even a surviving object becomes a locked message. Maya blue kept its message visible for more than 1,000 years. We are still learning how to read it. Every lost technology leaves different evidence behind: a tool, a text, a residue, or a color. Subscribe for the next investigation into ancient materials. Modern science is still piecing back together. The next forgotten process might be hiding in plain sight, just like this blue was.